Here's how to solve for apparent weight in a moving elevator. So a lot of times you'll be given some sort of problem involving an elevator that is either accelerating or decelerating, and asked how heavy a person feels, or what the scale would read. The key to solving these types of problems is to remember that the normal force is what's being measured when you step on a scale, and this force is directly related to how heavy a person feels, or their apparent weight. Let's consider the first case, where a 70 kilogram person is standing on a scale in an elevator, and the elevator is at rest. The first thing we do is draw our force diagram, which has the force of gravity pointing straight down, m times g, and an unknown normal force pointing straight up. This is what keeps the person from falling through the elevator floor. Now we use Newton's second law, F equals ma, to add up all the forces and set them equal to the mass times acceleration. In this case, we're going to call anything pointing up as positive and anything pointing down as negative. So when adding up all our forces, this gives us the normal force, Fn, minus the force of gravity, mg, which is all equal to the mass times acceleration. Now since the elevator is at rest, this means that the acceleration is 0. And therefore the normal force is equal to the force of gravity, which is 686 newtons. Note, this would still be the case if the elevator were moving at a constant velocity, because then the acceleration would still be 0. The last step is to take our normal force and divide by g, which gives us an apparent weight of 70 kilograms. This makes sense, because someone with a mass of 70 kilograms feels like they weigh the same 70 kilograms when the elevator isn't moving. Now let's say the elevator starts moving upwards and accelerates at 2 meters per second squared. Again, we're going to draw our force diagram, which has the same force of gravity. However, the normal force is going to be different, because now the acceleration isn't 0. Since the elevator is accelerating up, I'm going to draw an acceleration arrow in the up direction as well. If we look at our formula, we see that the sum of the forces now has to be positive, which since the force of gravity is always constant, this means that the normal force must now be bigger than the force of gravity. Plugging in our values and solving for the normal force, we get 826 newtons, which then dividing by 9.8 gives us an apparent weight of 84.3 kilograms. So in this case, the 70 kilogram person feels like they weigh heavier by 14.3 kilograms. Now let's say that the elevator starts slowing down as it reaches the top, such that it is decelerating at 2 meters per second squared. Again, we draw our force diagram with the same force of gravity. However, this time the acceleration is negative because the velocity is decreasing. What this means when looking at our force formula is that the normal force must be less than the force of gravity in order to get a negative acceleration. So plugging in our numbers, we get a normal force of 546 newtons. Dividing by 9.8, this gets us an apparent weight of 55.7 kilograms, which is 14.3 kilograms lighter than our regular weight of 70 kilograms. This is also why it feels easier to jump at the top of a rising elevator. And there you have it. That's how to solve for apparent weight in moving elevators.